Hello and welcome. This is the next part regarding matrix space, relation, Cauchy sequence and convergent sequences in matrix space. First, we write here the definition of convergent sequence in matrix space. Let M row be a matrix space and let Sn be the sequence of points in M. These points are in M. We say that sequence approaches L, where L belongs to M. Sn approaches L as N tends to infinity. If given epsilon greater than 0, when we say that if given epsilon greater than 0, there exists N belongs to I. When we say N approaches infinity, then there exists a capital N belongs to I, such that a row of SNL less than epsilon, a row that is difference or closeness between them, Sn and L, for all N greater than or equal to capital N. This expression can be written in this way also. Here we write limit of Sn as n tends to infinity is equal to L, or Sn tends to L as n tends to infinity. This total definition, meaning of this definition is, it means that sequence Sn is convergent in M and converges to L. And next definition is about Cauchy sequence. Cauchy sequence. Let M row be matrix space and let Sn be sequence of points in M. We say that Sn is a Cauchy sequence. When we say that Sn is Cauchy sequence, if there is epsilon, if given epsilon greater than 0, there exists N belongs to I such that row of Sn less than epsilon as N greater than or equal to capital N. Means M and N are large, Sm and Sn are very close to each other. M and N are big, large, then Sm and Sn are very close to each other. This is the definition of convergent sequence and this is the definition of Cauchy sequence. Now theorem related to these two, convergent sequence and Cauchy sequence, as far as matrix space is concerned. This theorem indicates that every convergent sequence is Cauchy sequence. But there are many examples such that conversion need not true. Every Cauchy sequence is not convergent sequence. This theorem is, let M row be matrix space. If Sn is convergent sequence of points of M, then this sequence is Cauchy sequence. By applying the definition of convergent sequence, let M row be matrix space and let sequence of points of M. Since Sn is convergent sequence, therefore apply our definition. For every epsilon greater than 0, there exists L belongs to I such that row of Sn L less than epsilon by 2. We choose here epsilon upon 2. Row of Sn L less than epsilon upon 2 for all N greater than or equal to capital N. And now, then for young N which are greater than or equal to capital N means big. If row of Sn L less than epsilon by 2, then also we say that row of Sm L is also less than epsilon by 2. Because small m and small n are very close, then row of Sm can be written as less than or equal to rho of SML plus rho of LSL. Here this is epsilon upon 2, this is also epsilon upon 2, hence we write the less than epsilon for all n greater than or equal to capital N. Means this is the definition of Cauchy sequence. Hence we say that every convergent sequence is Cauchy sequence. But here conversion is not true. It means every convergent sequence is Cauchy sequence, but every Cauchy sequence is not convergent sequence. These two are the examples, counter examples for this conversion is not true. First example, consider this space of real line 0, 1 with usual metric. Our usual metric form sequence Sn is a Cauchy sequence. This is the sequence Sn, which is a Cauchy sequence, and also it is converges to 0. Means no problem. But not convergent. But this is not convergent. Only this sequence is Cauchy sequence, converges to 0. But this is not convergent. And second is, suppose Q is the set of rational numbers. Then Q rho is the metric space, Q is the set of rational numbers defined by this rho of xy, mod x minus y, xy belongs to Q. Then sequence 1 upon 3 raised to n is a Cauchy, converges to 0. But there are many such a sequence 1 plus 1 upon n raised to n is Cauchy but not convergent. These type of examples indicates that conversion is not true. Some books use another symbols. These symbols are used in the Goldberg method of real analysis. Another examples, that is suppose Malik, book of Malik Arora, or you may say mathematical analysis, Malik Arora. In that, capital N, in place of capital N, they use small n0. And similarly, we use here Sn, they use Xn. Okay. Means symbols are different. We use here rho, they are in Malik Arora we use D. That is, symbols are different but meaning is same. This is the part of limits in metric space. Convergent sequence, Cauchy sequence, and relation between them. Like every convergent sequence is Cauchy sequence, but every Cauchy sequence is not convergent sequence. Thank you. Okay.